Yeah, because see, this is another example of which property. Yeah, this has to do with osmosis again. So when lettuce goes limp, is it because it's losing water, or is it gaining water? Those cells in the lettuce. So you're saying, is it, when I was teaching another class, Chem1B, we did this lab every semester, and I would forget how it would go because that's what math do. So is the water? So when lettuce goes limp, is the water going into the lettuce, or is the water leaving the lettuce? I'm not. So again, I can't remember. Is it leaving the lettuce, or is the water going in the lettuce and making it limp? Yeah, so what's going on there? Do you guys know? Because like I said, I can't remember. All those, every time I do the lab, I always have to ask. Water's going in? Well, if it's going in and out, then it's just like,
the water goes in that case,
I was going to put this experiment in lab 2. The lab we're doing this lab 2, but then one of the instructors said, "Oh, you students do this in biology, so no point in doing it in osmosis lab." So I guess that's what I get for listening to someone. That's why you guys are making coffee and try how to decaffeinate coffee. I said they're working with messing around with lettuce and celery. Would you guys rather have to do experiments with lettuce and celery or with coffee? Okay, so let's just assume that if the lettuce goes limp because the water is leaving the cell, how can we get water back into the cell?
Cold water.
Why cold water? So why cold water as opposed to room temperature water?
I know that's what chefs do. So yeah, I've seen them upstairs like in a bag with ice cubes in it.
Okay, so if somehow the water has left the cells of the lettuce, we can get water to get back into the lettuce. So are you going to put it in a salt water solution, or what are we going to do? We're going to put it in. Now again, if we put it in salt water, let's say put it in a 5% NaCl solution. Note that the water is going to leave the lettuce. So what do we need to do to get the water back into the lettuce to make it crisp again? Pure water? Yeah, you can put pure water. So if we put pure water in, the water should go back into the cell, and that's how we can make your lettuce or your celery crisp. Okay, so you can try that at home. Actually, what we did in the Chem1B lab is I think we started with crisp lettuce, and we put it in pure water, a 1% salt solution, a 3% and a 5% solution, and we observed what happened to the lettuce. And then once we made that observation, we tried to make it go backwards. Okay, so we went from crisp lettuce to limp lettuce back to crisp lettuce again. And then the other thing we can do is based on those observations, we can try to figure out how much salt was in the lettuce, whether it was 1% salt or 2% or 5% salt. So that was the experiment we did in Chem1B. But like I said, I've done that experiment like 5 times, and I still can't. And I never remember which way it goes, whether it goes in or out of the cell. Anyway. Okay, so let's go to this side. So again, if you add solute to water, the boiling point increases or elevates, the freezing point decreases or it gets depressed. And I think we did this calculation in lab on Thursday. So if you have 50 grams of salt dissolved in 1 cup of water, calculate the boiling point of the solution. Did we do this? Last we did. We didn't.
We did.
We didn't.
Okay, let's go over this again. So this will be the formula that's used. Delta TB, which is the boiling point elevation, equals I, which is the Van Hoff factor, times KB, which is the boiling point elevation constant, times M, which is molality of the solution. So again, I refers to the solute. Sodium chloride dissociates into 2 ions, a sodium ion and chloride, so that means the I value equals 2. So for a molecular compound, the I value equals 1. For an ionic compound, the I value is going to be equal to the number of ions that ionic compound dissociates into. KB refers to the solvent. So you can look up the KB water, and that's actually found in the textbook in chapter, let's see, chapter 13, and that's on page 450, table 13.2. So KB of water is 0.52 degrees per mole. So let me write that down. Okay, so we have on page 450, table 13.2. Okay, this is the KF and KB and various solvents. Okay, so anyway, KB for water is 0.52 degrees per mole. So in other words, if you have a 1 mole solution of any solute, that's going to raise the boiling point of water 0.52 degrees. Okay, so again, if you have a 1 mole solution, the boiling point of water is going to be increased or raised or elevated by 0.52 degrees. M is the molality of the solution. So molality is a little bit different than molarity. So molality is the moles of solute per kilogram of solvent. So we can calculate molality. So you take the moles of sodium chloride, you take the grams divided by the molar mass. So 50 divided by 58.5. Then you divide it by the kilograms of solvent. So 240 milliliters of water equals 240 grams of water, or 0.24 kilograms. So you take 50 divided by 58.5 divided by 0.24. That gives 3.56 molal. So then you plug it into this equation. So 2 times 0.52 times 3.56. So the boiling point elevation is going to be equal to. Okay, so with 2.52 is 1.04. 1.04 times 3.56 is equal to. 3.7. Okay, so delta TB is equal to 3.7 degrees. So that means that the boiling point of the solution, okay, so the BP of the salt, water, solution is going to equal 100 plus 3.7 degrees, and that's equal to 103.7 degrees. So like we mentioned last week, if you want to make your beans or your spaghetti cook fast, you add some salt to that pot of water, and as a result, the boiling point of that solution is going to be higher, so it'll cook a little bit faster. So 50 grams, I looked this up. 50 grams of salt is something like 10 teaspoons of salt. Okay, so let's go into question 2. Why is rock salt used to make ice cream? Now, let's see. Next Tuesday, 1 week from today, you're going to be making ice cream. So actually, let me put this down too. So for next Tuesday, Okay, so next Tuesday's lab. Okay, so you want to bring your whatever stuff you want to make nice and okay, so this means that you can bring like milk or cream, bring your favorite flavorings, bring chocolate chips, whatever you want to bring, and we'll supply the ice and the salt so you can make ice cream next Tuesday in lab. Okay, so you and your lab partner can figure out what you want to bring for your ice cream in lab. Okay, so anyway, why is rock salt used to make ice cream? And that's the boiling point. Yeah, freezing point. Now, when you make ice cream, what's the solvent in ice cream? Okay, so in ice cream, the solvent is, oh now milk is also a solution. So water, you have milk. The solvent in milk is water. Okay, so in these cases it's water. So we know that the freezing point of water is 0 degrees. So that means that ice cream or milk is going to have a freezing point equal or greater than or less than 0 degrees. Okay, so if the solvent is water, that means that the milk or your ice cream mixture is going to have a freezing point. Is it going to be greater than, equal, or less than 0 degrees? It should be less. Okay, that's because of freezing point compression. So, again, why do you use rock salt to make ice cream?